Hello, hello. Awesome. Okay. What? Hello, Fahima. Hello, Shasha. Hello, Anna. Hello, Grisella. Hello, Alex. Hello, Marlon. Hello, Almadina. Hello, Yulia. Hello, Kwan. Hey, Adriana. Good afternoon, Kareem. Hello, Noreen. Noreen. I'm good, thank you, especially if I pronounced your name right. I'm good, thank you. How are you? Oh, and also now a new thing, I have to say a special hello also to, interesting. Well, there's no videos, but I'm saying a special hello to Kareem, Shasha, Elena. Oh, I didn't even say hello to Elena, I don't think. Fahima, Yulia, Marlon, Kwan, Grisella, Noreen, and Anna for having not black boxes. Hello to you. Oh, and sorry, I didn't say hello. That and thank you. Good afternoon, Elena, which I hope I am pronouncing that right. And I hope I'm pronouncing, well, I hope I'm pronouncing everybody's name right at this point. It's kind of embarrassing if I'm not, isn't it? Okay. And my name is Yaverbaum, rhymes with cadaver town. Oh, good. Phew. Okay. Thank you. I appreciate that. Okay, good. Okay. Long time no see, sort of. Well, not really. Okay, typical long time. We are gonna, okay, we're gonna have a slightly unusual class. I mean, it's a long class. We're gonna make it a little bit, well, I was about to say the wrong, we're gonna take the whole time, but I think I do tend to drone on a bit often, especially in these 2 hour and 40-minute sessions. So we're going to break up and do some work first. I know that's what you always do in lab anyway. So maybe that's good news for some of you, maybe it's bad news, but we're going to break up and do some practice work. I know exactly where you are in lab right now. I know you've done motion 4. Wait, someone's here. I know we're getting you from the back door and the front door. We're hopefully starting to get used to this concept of harmonic oscillation. Wait, someone just came in, but I can't let them in. I mean, I can, but I can't. Oh, this is that administrator thing. Okay, we're going to have to ask this person to identify him or herself because it's so suspicious that it's administrator. Okay, hopefully they'll say hello to me before I have to get awkward, which I'm doing right now. Yeah, sorry. Okay, what we're going to, I know you're getting more used to harmonic oscillation, and I know that your motion 4 and your motion 4 report was all about harmonic oscillation, which is good. I want to get at it from a slightly different angle today. So we're gonna practice aspects of harmonic oscillation in groups, in breakout rooms, for good or for bad. I know some of us will enjoy that and some of us won't. I think the time will fly more though than if I just talk for 2.5 hours. And more people here. And what was I going to say? And there'll more clarity will emerge as to what we do and don't understand, et cetera, et cetera. This is going to be a little bit of what we used to call a board. Anyway, do you guys, have you done a board meeting yet in lab? Have you ever done or in 101? Do you know what I mean by a board meeting? Have you, or is that a, no, that's.
Yes, we have. Well, he gave us the information yesterday.
Oh, cool. All right. Thank you. Okay. So we're going to do sort of an adapted version. I mean, I'm a big fan of board meetings. I love board meetings. And thank you for answering. Oh, and that's many points. People just got points. You got points. Like, thank you. Like totally Kwan, totally Alex, totally Noreen, totally Anna. Thank you very much. Okay. For like actually answering my question. So good. I mean, now I'm a big fan of board meetings, and I used to do them all the time in regular physical space. I feel like they're like the best. I mean, I love that as a format for class. I still don't know perfectly how to work it through electronically or in Zoom. And plus, I know you're getting them with him in lab. We're going to do sort of an adapted version of a board meeting here. We're going to do like a boss meeting, like a boss fight, as in like this will be another level in our sort of pretense sometimes modeling our educational environment. Sometimes we model our educational environment after a courtroom or frequently in lab. Sometimes I like to model our educational environment after a video game. I mean, clearly, I'm willing to model an educational environment after just about anything other than an educational environment. In other words, I think classrooms work best when they feel like just about anything other than classrooms. And that is a feeling I've developed after living in the classroom for the last 27, how many years? 29 years of my life. So, okay, so what's going to happen? Okay, so what's going to happen? Also, I owe you a bunch of stuff. I have not forgotten. I'm going to catch up and start giving back some of that stuff also while this is happening. But what we're going to do in a minute, we're going to break up into groups in the breakout rooms, at which point I'll turn off the recording. We're going to break up into rooms in the breakout rooms, and I'm going to ask you to work on a series of questions in the breakout rooms, and then we're going to come back and share our findings and our results in the form of a discussion with many, many points to be distributed and given and traded all over the place. The questions that I want you to work on are right now going to be here on this screen. And you may want to take a moment to start copying them down, but I'll say this too, what I'm going to do in a moment, I'm going to just like walk you through the questions for a second. And then again, you're going to work on them in breakout rooms. I may, your main goal is to get answers to these questions, but you're not being great. You're certainly not being graded on answers to them or anything like that. The really main goal is to find out like which of these questions require a lot of thought and which ones don't. So don't stress. I mean, try to get answers. But if you can't get an answer to a question or you don't know how, try to engage in as much thought, clear thought, and written thought as possible as to exactly what difficulties you're having with the question or whatnot, because that's what we'll discuss when we come back. Oh, wait, weird. Hold on a second. Yeah. Wait, thank you. Wait, totally. Thank you, Hannah, for doing that. But wait, I'm so psyched that Hannah just did that, but I'm a little, are you doing that for the benefit of everybody? Is that the point?
Yeah, you can see the chat when you're in the breakout room. So if anyone just missed a question, I figured.
Oh my God, that is so, wow. I'm like stunned. I have to like create a whole new point portal just for, I don't even know how to categorize that bit of generosity. Like that is like really nice. Okay, that's really cool. I'm like literally stunned. Cool. Then I'm gonna keep scrolling through, and she can wait. And that's really, actually, that's really true. The chat gets preserved even as you go into the breakout room. You're saying even old chat will stay frozen. Like the chat doesn't start.
Yeah, you can still see the chat from the entire group when you're in the breakout rooms.
Wow. I didn't even know that. That's okay. Well, this is great. I'm glad she's doing that. Then I'm going to scroll through and let Hannah continue. I'm going to totally appreciate that Hannah's going to continue to do this for the next set of questions. What I was going to say that I'm also going to drop the PDF in for all of you, like the PDF of these notes for all of you, so you can retrieve it in Google Classroom while you're in the breakout rooms, if that helps. But what Hannah's doing is probably even better, but I'll do that too. But okay, and I'll make the breakout rooms momentarily, but again, but here, this is like a board meeting, or we're calling it a boss meeting, as in a boss fight. In that, again, though, just bear in mind in the back of your mind, you're not handing in these answers or anything like that. The real purpose is for us to have as productive a discussion as possible when we get back. And by productive, I really mean this too. Remember, for some of you, I speak too fast, and for some of you, I speak too slow, content-wise, right? I mean, I go too fast. For some of you, probably not many of you in this room. For most of you, I probably go too slow. But it's partly because I never know exactly what you need to hear, what you're clear on, or what not. So really remember that when you're in the breakout rooms, your real objective kind of is to get these questions and really, like in private, without me hovering over your head, find out what it is you really need to find out, when we come back. You know what I mean? So when we come back, like if all of you are like, yeah, like 1 and 2 were easy, like please don't waste our time. We got it. But then if like 3 and 4, that's where we need the discussion. That's what we're going to find out. So your goal in the breakout room is to really find out what it is you need to find out. And then that's what we're going to share and care when we come back. Okay. So it's like, and I'm not going to really answer that many questions, if at all, while you're in the breakout room. So it's really about figuring it out, how we can all figure this out together. Okay, I guess you get the, I'm sure you get the point. So that's it. All right. So yeah, you're supposing, and also if we're going to go with the Hannah thing, like, if we're going with the Hannah thing, all the questions are going to be based on this scenario. So I guess that's number one. But if we're numbering things, everything coming in from here on in are really the numbered things. The scenario is you've got a harmonic oscillator described by this equation, x equals 5 cosine of 6 pi times t. By oscillator, I mean something going back and forth, whether it's a mass on a spring or a bob on a pendulum string. By harmonic, I do mean that word that I know you were studying in motion 4 with Walters and everything yesterday. I do want to quickly point out, I'm not assuming that you're 100% fully confident and straight on exactly what harmonic means. I'm assuming that that is what you're probing right now with him, and that we're going to be able to flesh that out even more today. But suffice to say, we're certainly picturing an oscillator of sort of the type that we've been studying in class. So assume there's an oscillator that's going back and forth on some x-axis. And you can assume, I should say this for the following questions. I'm sorry, I don't know if I was going to add this or not. You totally can assume that x is measured in meters. So perhaps this is a mass going back and forth on a string, on a spring would probably be the easiest thing to picture. And you certainly can assume, should assume, that t is a time measured in seconds. Okay, so you have this oscillator that, and this kind of equation is the kind, I should also say, that I feel like we derived or we conjectured and verified last week in class. Like we came to the view by finally finishing homework 1, that if you want to describe or predict the position of an oscillator as a function of time, that a cosine function of this form is the right way to do it. Like you may, in other words, want to consult your notes from last week as to sort of where I'm even getting this from or why, but this is the format for an equation that describes the position of a harmonic oscillator, right? And if it were like a pendulum on a string, perhaps then x wouldn't be x, perhaps it would be theta measured in some other units or something, but you can assume that we've got something going back and forth. All right, I'm talking enough. So assume that that's the given, that we've got an oscillator going back and forth, described by that equation. Then the questions are these. And again, I mean, if Anna could put these in the chat, that's great, but I will also pass this PDF around. So here we go. Oh, cool. I'm so, oh, now funny. Oh, Yulia's question.
I didn't know it was going to be the question.
No, but that's great. That's your, and you can't even read my handwriting. That really says something, that's like the best. I should open up a portal for that too. I'm trying to remember all these portals that I have to open up. That really says something. And again, I don't want to I don't want to spend the entire class praising Hannah or the entire class praising Yulia, although why not? I mean, I don't mind doing it. No, but like, obviously they're not the only ones in the room, but I do want to say that now this thing that Yulia just did, that really she does deserve credit, because of course she wasn't cheating. And of course she didn't know what I was going to ask, but the only thing better than like knowing the answer to a question that is coming up is actually being able to anticipate the very next question. Like that really does show. I mean, she's thinking like, I can't say it enough, but like, if you could predict the questions that are going to be on an exam, right? Like you really know what's going on. So she's totally right. And so, yeah, I'm not going to answer it. I'm not going to answer what Yulia asked, but I can definitely say she is the opposite of crazy to have asked it. But the fact that I'm not answering it, or the fact that I made it one of the questions, does mean I do think it's answerable. And if nothing else, partly look at your notes from last week, that might help. I will also give this hint. Actually, I should say one thing that kind of is important. In general, you're used to taking the cosine or the sine or the tangent of angles like that. I think it is fair to assume that generally in a math class or whatever, when you guys take the cosine or the sine of something, you are taking the cosine or the sine of something that you generally regard to be an angle. Now, angles, I will say, can be measured in degrees. They can, but they can also be measured in something called radians. Ultimately, the two are equivalent ultimately, but they each have, oh God, a lot of people are coming in. But there's advantages and disadvantages of each when it comes to convenience. So I am going to say, this is almost answering Yulia's question, but not quite. I do want to say from here on in this physics context, you can assume that whenever we're measuring angles, we would prefer to use radians. Like we would prefer radians over degrees. And I'll even say, therefore, that when you start trying to get answers to some of these questions that you're going to see on the next page, do put your calculator into radian mode, not degree mode. Now, I will also, now that does not answer directly Yulia's question. Let me be very clear. It gives a huge sort of leg up or hint or help as to what the answer to Yulia's question is. But it is not literally the answer to Yulia's question. What I am saying is you can assume that whenever we're talking about any kind of angle, or you can assume that when you take the cosine of something in this class, that something will be in radians. But please do note that what we have in parentheses there is like a number times a t. Like there's a lot going on in that parentheses. So honestly, the answer directly to Yulia's question is not just radians. It's something based on radians, for whatever that's worth. Last thing also, and maybe I'm stalling here so that maybe Hannah is copying on these questions into the chat, I'm not sure. But I always want to say to everybody, part of the reason we're going to do this practice exercise stuff today is I am assuming we have to use radians. I am assuming you've seen them before in a math class, or like that I'm not surprising you when I say that we're in radian mode, but I'm also in the back of my mind, I am not assuming that everybody's perfectly comfortable with radians. I am not assuming that everybody likes radians. In fact, I'm assuming the opposite. I'm assuming that they're probably, if it were up to a lot of people in the room, you would prefer not. Like if you're anything like me, if you're anything like I was back in the day, if someone said radians, my brain would fuzz over. I could sort of do them if I had to, but I didn't feel comfortable with them at all. They didn't make anything clear to me. And I didn't really know what I was doing when I was dealing with radians. If you are in that state, I'm here to ultimately, hopefully help. So, but we can only help by practicing and getting used to them. So I will have a lot to say about radians by the time this class is done, if Walters hasn't already. But yes, so don't assume that I assume that you're straight with them, but I am assuming that that's what we're using. And that is a big hint to answer Yulia's question. So, okay, we look in the chat. Okay, yes. So thank you, Hannah. That's awesome. Right. Okay. So again, these are the questions you're going to answer in your groups. Maybe some of you are already answering them in your head. That's fine too. But then you're going to share with your partners. And they are in the chat, but then there's more coming. And then I will also share the PDF, but here we go. So there's that. All right. Then the next page here is boom. Come on, go, 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 magic, go. There we go. Okay. So then, and then none of these is supposed to be a trick. As you could tell, they're kind of quick and dirty questions. So some of them, and whatever, they're like exercises. So don't overthink them. If you think you get it, then you get it. How many cycles will this oscillator perform per second? Then the next question, in hertz, what is the standard frequency of this oscillator? Oh, this is so fun watching it like turn into type. Thanks to Hannah, right. And I'm going to tell you a hint right now for those people who I'm totally boring to tears or driving crazy. If you're still paying attention right now, I'm going to tell you right now, the answer to number 5 right here on the page is the same as the answer to number 4. Just a checkpoint as you're going along in this boss fight. If you're like, question 5 is being asked to kind of reinforce and show everybody or make it clear that that is a different way of asking the same question. That is what is meant by standard frequency. So I'm telling you right now, if you're paying attention, whatever you get for number 4, that is also what you should write down for number 5. In that sort of the point I'm trying to make. Okay, cool. So oh, she even wrote that. Okay, wow, that's a free, you've got a good friend in that friend right there, all of you. Now I'm totally, all right, I'm gonna go to the next page now. And it's not going to go forever. Or, oh, sorry, I guess I lost the next page. Here we go. Then. my handwriting. Okay, so 6 and 7 is a pair, kind of just like 4 and 5. For those people who are paying attention, either to him or to me. Oh, more people coming in. Like 7 is just the more technical way of putting what is being asked in 6. I'm just trying to first ask it in a way that sort of like makes sense, maybe intuitively, but then that's, so if you get an answer to 6, then you should, right, okay, yes, exactly. So 6 and 7, okay. And as I'm sure you're gathering, and I'm sure you've experienced in physics before, all of you, each one of these questions is kind of building off the ones prior. None of these are supposed to be a trick. None of them are supposed to be that hard. But if you just dove in and tried to do number 7 without doing 1 through 6, it might be more challenging than if you just proceed in order, okay? And we're almost there. I'm going to stop me if you want, if you're also copying them down, but I'm going to go to the next page. I don't know why the page just got erased, but. Yeah, okay. Right. Oh, so. Okay, there's going to be one more question. There's going to be one more question, but I wanted to, because this is like hideously illegible. And it, oh, that was fast. Oh my God. Wow, she's really fast. Okay, I was about to say it's hideously illegible. It's now not, thanks to Hannah. But I do want to clarify something about this question, or this is where we're about to get, into the punchline of this whole thing. There's going to be one more question, which is the real punchline. But I do want everybody to notice, by the time you get to question 8, and you should, discuss with your group and come to a view, notice that the question of question 8 is it possible? Why or why not? In question 8, it's not your responsibility yet to figure out the stiffness of the spring. I mean, it does ask, using any or all of the above info, is it possible to determine spring stiffness? Like, your answer is either yes, it is possible using the above information, or no, it is not. If you think it's no, and then it says why or why not. If you think the answer is no, it is not, then you should come up with some kind of reason, right? Or, well, yeah, some kind of reason. If you think the answer is why, yes, then yeah, you should still come up with some kind of reason. Maybe you even think that you know a method, so you could even say the method, but it's not your job. In order to explain why or not, you don't necessarily have to find the spring stiffness, is what I'm saying here. You just have to say whether you think it is findable or not based on the information we have. Okay, just want to make that clear. That's oh, sorry.
For this specific question, can we assume that displacement, that we know the displacement in the position of the spring? Or we cannot assume that we know it?
Oh, that's a great question. That's a really great question. Okay, and that will, I have to be careful. That's like your other question. I'm gonna have to be careful about answering that because it's such a is a relevant question that I don't want to over answer. But my real answer is it depends what you mean by when you say can we assume we know where the spring is? Well,
can we assume that we know, like you provided us with information about the mass, 2 kilograms. Can we assume the initial position of the spring at equilibrium, and then after the mass is attached to it, so we could identify the displacement of the spring after you attach the mass to it? Can we, or like, you know what I'm saying?
I do know what you're saying. No, I think it's a great question. So let me I don't know that this is not a vertical. There's a couple of things I think you're thinking about. I think you're partly basing what you're saying on lab 1, which is very smart that you're doing that. But I believe this is not a vertical spring. This is a horizontal spring. So let me put it this way. I believe you can't assume, but I believe if you answer all these questions correctly, or you start going through the questions, you'll see that somewhere in here, I think you do know. I think I did, in fact, sort of implicitly tell you where the mass is initially. Like I think you do know that, or at least you'll see that you know that as you start going through the questions. I do think you have the information of, I mean, again, I have to be careful I'm saying this because I might sort of accidentally give away the answer to one of the questions if I say too much about this, but I do believe you're going to find, as you're answering the questions, that you do know where this mass was when this whole thing started, i.e. how far from equilibrium it was. Now, to be clear, or to be fair, this is an oscillator. So it's like going back and forth and back and forth. So I don't think it's always going to be there. Like this isn't a vertical spring that's just like hanging. This is a horizontal spring that's going back and forth. But yeah, I do think that you know, or you will know once you're answering the questions, where the mass was initially. So I think that's my answer. I think that's a very interesting question. I'm not going to give you any more information explicitly telling you where the mass is initially, but I do think you do know. What I'm also going to ask, wait, sorry, did I answer? Let me make, it is a really good question, but I'm being cagey, I guess. So I'm not, did I answer the question or not really?
Yes, you did. Thank you.
Okay. All right, and again, with all of these guys, I mean, seriously, I think you can tell, I hope you guys can tell, like, the more I can't really answer a question, the more it probably indicates that it really is a good question, if that makes sense. I'm just like trying not to give away the farm here. But there's one more question I'm going to put on a sheet, and I'm going to shut up, and then I'm going to put you in break rooms. I'm going to work on this. And the question is this. Okay, this is a two-pager. Sorry. I don't know what Hannah's going to do with this. I'm just going to read this out loud, and I'm going to go to the next page. I'm saying on this page, in general, the angular frequency, omega, okay, which is really what we're kind of studying here. We're kind of studying it because I think it's the newest term in all of this discussion. Omega, oh, well, I don't want to say much more, but the angular frequency of an oscillator, the cycling rate of an oscillator, which we call omega, and again, that's in your notes from last time, which we call omega, the rate at which an oscillator goes back and forth and back and forth. It must depend on whatever we can measure, the properties of that oscillator that we can measure and we know and are constant for that oscillator. Like one oscillator oscillates at a rate that's higher than another oscillator. Why? Well, it must be because of certain properties about that first oscillator compared to the second, right? Well, there's a finite list of how many properties we could possibly even list or identify for any one given oscillator. So what I'm going to ask you guys to do is from that list, figure out which one of them are determining the angular frequency and how. In other words, this. So I'm going to the next page. Tell me if you want, or I'm looking at Hannah. Okay. Okay. All right. Okay, this is the hardest question of all. This is ultimately the point of the whole thing. I mean, just to be clear, this might require or engender the most discussion. But what I'm saying here is omega, the lowercase Greek letter omega stands for angular frequency, the rate at which the oscillator cycles back and forth, back and forth. It's measured in certain units that I think you're asked to find in one of the early questions of this assignment today. And it's also, again, this is all in the notes from last time, if you check or if you have them with you, but omega is angular frequency, the rate at which the rate at which the oscillator cycles back and forth and cycles back and forth and back and forth. If we know angular frequency, then from it, we get other things such as standard frequency and period. That's what you're being asked to do in the early questions. Those questions are trying to help you sort of get your mind around exactly what angular frequency is or how it works. But anyway, angular frequency is the rate at which an oscillator goes back and forth, back and forth. Now, what I'm saying is at some point in the early questions, you're being asked to establish what the units of it are. Sort of Julia sort of already asked that, but I haven't fully answered it. So you're being asked to establish what the units are. Once you've done that in the early questions and you have the units of angular frequency and you've sort of played around with them a little bit, then what I'm saying to you is, okay, look, this angular frequency, it's got to be determined by something. Like one oscillator will cycle at a faster rate than another because one oscillator has certain properties that another one doesn't have. Like either it's heavier or it's less heavy or it's stiffer or it's less stiff. But they're the only properties that we actually, the only properties that distinguish one oscillator from another are the three that keep coming up in all these discussions. K, the spring stiffness, M, the mass on the spring, and then X naught, the initial position or the initial displacement from equilibrium. Again, kind of the thing that I think Julia might have been asking about, toward the end. Those are the three constants that we've ever identified as being describing an oscillator. They're the three numbers that were given in homework 1 to describe that mass on a spring. Now, I'm saying each one of those has certain units associated with it. I'm not going to say what they are right now, but I mean, you have them in your notes, you can think them through. Each one of those has units. What I'm asking you to do, and this is not easy, but it is doable. I'm asking you just to play with the units of those three and figure out which ones of those three have to be put together in order to make, which one of those three constants get put together in order to determine omega, and how are they put together? Put another way of saying there must be an equation. There must be an equation between omega that sets omega on the left side and puts some combination of those constants on the right sides and put them together in some kind of a way to make omega, because omega must be determined by the measurable constant properties of an oscillator. Now, let me be clear again. I know I'm dragging this out. What else is new? I'm dragging this out. But I am guaranteeing you, it's not a trick. I am guaranteeing you that there is a certain combination, like it might be X naught divided by M, or it might be M minus X naught. There is some combination. There is some comparatively simple combination of some of those that if you put them together, the units will work out and give you the proper units of omega. There is. Now, I'm definitely not saying that it is necessarily all three. In fact, I'm even saying it's not all three. Part of your job is to figure out sort of which one or two of those three is together making omega. You're going to do this purely from units, as long as you're actually clear on what the units of omega are, and as long as you're actually clear of the units of those. Then again, when I say it's not a trick, what I mean is in the simplest, I guarantee you that if you're clear on the units, then omega must be formable by the simplest possible combination you can imagine of some set of the other three that make the units work out. The trickiness is sort of knowing the units of all and being able to play with units. But if you can find a combination of units from some set of those three that yield the units of omega, then you have found the equation that relates measurable properties of an oscillator to omega. Let me warn you of a couple further things. Now, again, I don't, this is hard. I mean, it's totally doable and it's not calculus. I don't think this is easy, and it is the point of all the other questions, but it's not hard in some sense that like you need a calculus class or even like really a trig class. It's not that you need other math to do this. You just really need to feel comfortable with the units and feel comfortable playing with units. There's no numbers involved at all. It is pure units. And this would be an exercise that might be really fruitless if you didn't know for a fact that there actually is, and it actually does work. And I am telling you that, like there is an answer. The last thing though is, what I know is, if you're really paying attention, you're really hearing me, some of you might already know an equation for omega. You might already know how omega is dependent on some combination of those three. You might know that from Walters, or you might know because you went because of the internet. And I don't want you to erase knowledge. I'm not trying to tell you to not know something you already know. If you think you already know an equation that gives you omega from some of those letters, then Quark bless America, that is great. If you already know that, you can share that with your partners in the breakout room. It's not cheating, but that'll give you a leg up if you think you already know. But what you have to do then is regard this as a proof. You have to show yourself and your partner, and ultimately me, you have to show that equation makes sense from a units perspective. So like, whether you're constructing that equation for the first time, discovering it for the first time, or getting frustrated, giving up, finding the equation on the web, and then retrofitting this, that I don't care. But what our job here is to show ourselves that units alone can make that equation make sense, or can make that equation for us. So your job is to relate omega to some combination of those three things. Also, if you don't like units, you can just start by backing up and saying to yourself, like, what should it? I'm even telling you in advance, one of those three things does not determine omega. The other two do. You might just use your intuition, your reasoning, like, well, what Yaverman was really asking is like the rate at which an oscillator goes back and forth, is it determined by stiffness at all? Yes or no? Does it seem like it should depend on mass at all? Yes or no? Should it depend on like how far the spring is stretched? Yes or no? Like you could totally be intuitive about that, but what will ultimately verify for you and rigorously like ground your answers will be the units. Okay, so that's the hardest question of all. Sorry to explain it so much, but I think it does require some explanation. Again, it is the purpose of this whole exercise, but I think it'll be a lot easier to see and you'll have much more of a chance, and we'll have a much more coherent discussion about it if we go through all the warm-up questions first. So, okay, I'm looking, right. Oh, good. Oh, sorry. Okay, wait. So I'm going to look in the chat for a second and I'm going to shut up or make sure. Wait, so I'm looking, so Hannah that's great. Okay, so Hannah totally, thank you. She totally did capture this whole thing perfectly. And I will submit the PDF as well, but then Shasha's question, great question. Well, the answer, so Shasha's question is down here at the bottom where I've written K and M and X naught. She's asking, is M mass or is it meter? Good question. It's actually mass. And here's how I know, because I didn't write, like the other two are not written as unit, like X naught would be measured. Well, I shouldn't say actually, but okay, it's mass. M stands for mass, not meter. Those three letters are standing for constant measurements that have units associated with them, but it's sort of your job to know what the units are. So yeah, K stands for spring stiffness, as in the K, as in F equals negative Kx. M stands for mass on the spring, and X naught stands for the initial position of the spring, of the mass on the spring, or more specifically, where the mass, how far from equilibrium the mass was stretched when it was held at rest and released. Like X naught assumes a position at which the mass is at rest somewhere other than equilibrium. Okay. Oh, okay, cool. Oh, good. Thank you for circling. She totally just closed a conversation. Okay, so this is the question. I mean, these are the questions. I'm gonna put you in breakout rooms for a minute, and you're gonna take a while. I hope. And I'm not really going to answer. I'll answer clarification questions, stuff like that. But basically, I'd like you guys to work this on your own. I might even scramble up the rooms at one point. Certainly, let me know if you think you're done. I mean, but if other than being done, well, please do let me know when you think you're done. But other than that, just keep on keeping on. And I will be here. I'm not going anywhere. But I will be trying to turn back your work while we do this. Okay. So I'm going to put you in breakout rooms. Are there any other questions? Does this make sense what we're doing? And we'll probably take, what time is it? We will probably take a solid. Well, I think this is going to take at least 40 minutes, probably. I mean, well, we'll see, but it is what we're doing. Okay, are there any, is it clear? Like, oh, can I just get, like, how about this? Show of hands, show of electronic hands, if this is sort of clear what we're about to do. I mean, it doesn't mean you have answers, but can I, yeah, oh, cool. Thank you, Alex. Thank you, Shasha. Thank you, Yulia. Thank you, Diana. Thank you, Anna. Thank you, Fahima. Thank you, Almadina. Awesome. Could just everybody do it as long as you're clear at all. Okay. Thank you, Grisel, and just keep them up. Like, just so I can make sure. Just keep your hands or your electronic thumbs up if it's clear. Sorry, I just want to see. Like I don't want to. Great. Like Adriana and Ivana, is it clear? Or oh, cool. Thank you so much. Or awesome. Oh, and I have to ask one last thing. Sorry, not to embarrass any. It's great. So it looks like it's clear to everybody. I totally appreciate it. One last thing. This is a little bit awkward, but administrator, could you maybe either in the chat or in the private chat tell me who, like, I assume that's just the name of your device, and I assume you're a person that I do know and is in the class, but I do kind of have to make sure that you're not. Oh, okay. So, right. M stands for mass. X stands for position, right? Right. So K stands for spring stiffness, measured in units that I can't tell you. I mean, M stands for mass, measured in units that I can't tell you. X naught stands for initial position or initial displacement from equilibrium, measured in units that I can't tell you. But wait, oh, is that yours? Oh. Yes, correct. But administrator, can you tell me who you are? Or are you just a second device of somebody else? Maybe you don't know that you're. Oh, okay, great. Thank you. I appreciate it. Sorry, just to make sure, I have to make sure this is a safe learning environment. Okay, thank you. Right, of course. Okay, okay. I appreciate it. And that counts as points for circling back a conversation. Okay, so we are going to go into breakout rooms in a moment. I'm going to set them up right now. One.
Professor, can I ask one more question before we go?
Yes.
Like question 6 asks how many seconds will it take to complete one cycle? And question 7 says, what is the period of this oscillator? Isn't it the same thing?
Yeah, no, totally right. I was trying to say that before. Yes.
Okay, sorry. I missed
Totally.
it.
So, you're right. There's two pairs of questions in there where definitely, if you understand what's happening, you should get the same answer to both, because it is literally and intentionally two different ways of asking the same thing. You're absolutely right. Because I'm just trying to show that to everybody. Basically, I want everybody to see, like, if you get one, then you get the other. There. So yes, totally yes. Okay, I'm gonna make a good point. All right, I'm gonna make. No, thank you. Good call. All right, I'm gonna make breakout rooms now. And if it says that I'm in your room, it's lying. Okay, here. All right, so please go to your rooms and good luck, Godspeed. I'll be visiting from time to time. Oh, and Marlon, did you get a room assignment? Marlon, are you okay? Marlon, are you there? Marlon?